Okay, so we continue with our uh, periodic properties, that is the fifth module. In the last lecture, the first lecture of these periodic properties, we learned about effective nuclear charge, penetration of orbitals, variation of orbital energies, electronic configurations, right? In this second lecture, we shall discuss about the atomic and ionic sizes, ionization energies, electron affinities, and electronegativity. These four concepts are not new to you because you already studied in the higher secondary level, but we'll discuss few other aspects in details, and maybe we'll come out with some new ideas also. Nearly 100 years ago, Rutherford showed that most of the mass of an atom is concentrated in its nucleus, and the rest of the part is essentially void. Now we know from our discussion from the first module of quantum mechanical atomic structure that the volume of an atom is taken up primarily by its electrons occupying quantum mechanical orbitals. We also saw that these orbitals do not have a definite boundary but represents only a statistical probability distribution for where the electron is found. So, how do we define the size of an atom? One way to define atomic radii is to consider the distance between non-bonding atoms, that is in direct contact. For example, krypton, that is an noble gas, can be frozen into solid in which the krypton atoms are just touching each other but not bonded together, right? This is important. We have to know that they are not bonded together, they are just touching. So it is a non-bonding distance. Now this distance between the center of adjacent krypton atoms, which can be determined from the solid's density, is then twice the radius of the krypton atoms. Then the atomic radius determined by this way, by dividing the interatomic distance, is called the non-bonding atomic radius, or more commonly the van der Waals radius. The van der Waals radius represents the radius of an atom when it is not bonded to another atom. Another way to define the size of an atom is that what is called bonding atomic radius or covalent radius. It may be defined for nonmetals and metals differently. For nonmetals, it is considered to be the 1/2 the distance between two of the atoms bonded together. For example, the distance between bromine atoms in Br2 molecule is 228 picometers. Therefore, the bromine covalent radius is assigned to be 1/2 of 228, that is 114 picometer. On the other hand, for metals, this covalent radii is 1/2 the distance between two atoms next to each other in their crystal structure of the metal. Right. Now, if you see the picture, it looks more like non-bonding krypton solid, but it is in this case these metal atoms are not non-bonded to each other. They are bonded through metallic bonds. Right. Okay. Now, using this method, we can assign radii to all elements in the periodic table that form chemical bonds or form metal crystals, and by this way we can derive at this kind of graph that we more commonly see in any books. A more general term, the atomic radius referred to a set of average bonding radii determined from measurement of large number of elements and compounds. The atomic radius represents the radius of an atom when it is bonded to other atom and is always smaller than the van der Waals radii. Right? The approximate bond length of any two covalently bonded atoms is the sum of their atomic radii. For example, the approximate bond length of ICl is iodine's atomic radius, that is 133 picometer, plus chlorine's atomic radius, that is 99 picometer. right, and calculated to be 232 picometer, and experimentally determined bond length of ICL is very close to is, and it is found to be 232.07 picometer. Now if we look at this picture or graph of the atomic radii of the first 57 elements, some general trends come out, okay? And these are same as that are observed for van der Waals radii also, right? So they will be in the same trend, the van der Waals radius as the atomic radii. Now what are these trends? You easily see that the peaks are occupied by the alkali metals, right? And the bottom half is by the noble gases. Now this means that as we go down the column in the periodic table, the atomic radius increases. And secondly, we can say that as we go right across a period or the row in a periodic table, the atomic radius decreases. Now we can easily understand the observed trend in radius as we move down the group. The atomic radius is largely determined by the valence electrons, the electrons farthest from the nucleus. As we move down a column in the periodic table, the highest principal quantum number, that is n, of the valence electrons increases. Consequently, the valence electrons occupy larger orbitals, resulting in larger atoms. The observed trend in atomic radius as we move to the right across a row or a period, however, is a bit more complex. To understand this trend, we now have to revisit the concepts that we learned in the previous lecture, that is effective nuclear charge and shielding. Now, the trend of the atomic radii as we move from left to right of the periodic table is determined by the inward pull of the nucleus on the outermost electrons, right? So more the pull, more shorter will be the radius. Now as the Coulomb's law tells you that it is directly proportional to the amount of charges, right? So more the charge on the nucleus, more will be the pull. Again we come to that effective nuclear charge concept, right? Now let us clearly see the example of hydrogen and say helium ion. Both of them have the same configuration, right? But to remove this one electron from hydrogen, we need only 1312 kilojoule per mole. Whereas this one electron, if you want to remove it from the positively charged helium atom, right, it will require very high energy. Now why this is so? This is because this helium has 2 units of positive charge, whereas this hydrogen have only 1 unit of positive charge, right? That means this electron, one electron, the outermost electron of hydrogen experiences only the attraction of the unit positive charge of the nucleus, whereas the outermost electron of the helium ion, right, not helium atom, this helium ion actually experiences double the positive charge from the nucleus with respect to hydrogen. That's why the difference. So consequently the R covalent of hydrogen is very high than that of helium plus, right? That's why it decreases. Now if we do a simple calculation for the next one, because this is the simplest example, let's do the case of say lithium and beryllium. So it's 3 and 4. So what is now the electric configuration of lithium is 1s2 and 2s1, whereas that of beryllium is 1s2 and 2s2. Now by Slater's rule we can easily calculate the shielding constants. So for lithium it will be 1 multiplied by it will be 2 multiplied by 0.85 for these two electrons, right, which will amount to 1.7. okay, now we don't have to add anything here because it will not be counted. There is only one electron for lithium here, so it will be 0. But for beryllium it will be 2 into 0.85 for these 1s electrons, and now we have 2 electrons here, so there is one more electron than the electron we are considering. So we have to write it here, 1 multiplied by 0.35. So it will be 1.7 plus 0.35, so it's 2.05, right? So now let me put it here. The Z effective for lithium will be 3 minus 1.0, so it is 1.30, whereas for the beryllium 2s electron, right, for 2s electron, they are both are for 2s electron. So for beryllium Z effective will be 4 minus 2.05, so it will be, so it is clearly seen that for beryllium, though the shielding constant increases due to the presence of the one more electron in the 2s orbital, right, and due to some repulsion, still the effective nuclear charge on the outermost electron has increased, right? So that's why we can say that the outermost electron of beryllium is more tightly held than that of lithium, and consequently it results to what? The radius of lithium is larger than radius of beryllium, right? That means as we go from left to right, the radius decreases, right? Similar calculation if you do for all those up to neon, you will derive the same conclusion, right? Why it is so? Because the extra electron is being added in the same cell, so that will contribute to shielding only minutely, that is 0.35, whereas you have, as you go from left to right, you always add +1 in the nucleus. So for the nucleus you are adding +1, right, and for the electron in the same cell you have to subtract it by only 0.35. So overall there is a gain of 6.5 nuclear charge, effective nuclear charge, as you go from left to right. That's why the pull on the outermost electron increases and the atomic radii decreases. Now this is the explanation for the steep decrease from lithium to neon or from sodium to argon, right? Now if you see, now this part, if you look at this part, what is this? These are the transition elements. You see, for the transition elements, for the first two it is decreasing as expected, right, as expected, but then suddenly there is slow decrease. It is decreasing a little bit, but the rate has become very less, right, and more or less you can say they are remaining constant. And moreover you can see for the last two, that is copper and zinc, they have actually increased in size. Why this is so? Why? Can we explain it? Right? Now you can do this by effective nuclear charge as well, right? For transition metals, right, what you have? A 3dN and a 4s2 type of configuration, right? Now which is the outermost shell? Of course this one. Now and who determines the atomic radii? Of course the outermost shell. Now as the outermost shell and this configuration remains same for all of them, right? For all of them this is constant. So that remains almost constant, right? Now this is one part of the story. The other part is, see, as you go from left to right, say from 24 chromium to 20 from 25 chromium to 26 iron, what is happening? The next electron is coming in the d orbital, right? It is coming in the d orbital. Now as the next electron is coming in the d orbital, what is its contribution to shielding? See, as per Satter's rule, the contribution of an electron in shielding, if it belongs to the next lower level n minus 1, this is what? This is n minus 1th level, right? From here 4 to 3. If it is n minus 1 level, then the contribution is 0.85. So for each electron added in d orbital, you have to subtract the nuclear charge by 0.85, whereas as you go from left to right, you will be adding only one positive charge in the nucleus. So overall your screening or the effective charge or the shielding constant will increase by what? Or the effective charge will increase by 0.15, right? So you see, for the main group elements it was plus 0.65 increase, right? This was the increase in effective nuclear charge as you go from left to right of the periodic table for main group elements, say from nitrogen to oxygen, right? Or say so as we saw that from lithium to beryllium and so on. But for transition metals, right, the increase is only 0.15. It's very less. That's why they decrease in size very slowly, or rather they remain constant. And moreover, for the copper and zinc, the configuration is 3d10, right? For this field configuration, due to electronic repulsion, the size actually increases a bit rather than decreasing. Okay. So this is the discussion about our atomic radii and how they changes in the periodic table. Next is our ionic radii. Now ionic radii, right, is very interesting to note. Suppose we have examples, say fluorine and sodium, right? So what is the number of electrons here? It's 9 here and it's 11 here, right? Now what type of ion fluorine will form? Fluorine will form, of course, uninegative ion, because it will more quickly try to capture one electron in its shell and form the octet type of or the noble gas configuration. So if you have F minus, F minus, right, that have 10 electrons, whereas so you add one electron here, it becomes 10, and if you have Na plus, that has also 10 electrons. So they are what? They are isoelectronic in nature, right? They have same number of electrons. So if you write the electronic configuration, it will be 1s2, 2s2, 2p6. So this is the electronic configuration for both fluoride ion F minus and as well as the sodium ion, sodium cation, right? So same number of electrons are present here. Now let us calculate the shielding constants for this configuration for an electron in 2p. So for a 2p electron, S becomes what? 0.85 plus 7 multiplied by 3.5, right? So it will be 1.7 and it's 2.45. Okay. Now if you add these two, it becomes 4.15. Now this is the shielding constant. Now with this shielding constant, if you calculate the Z effective on 2p electron for F minus and Na plus separately, what you have? The Z for F is still 9, be it F minus or F, the Z is same. Now you subtract from it 4.15, and for sodium it's 11. So again you subtract 4.15. So in this case you have just 4.85, whereas in this case you have 6.85. So you see what you have. You have a very loosely bound electron in this F minus ion, whereas very strongly bound outermost electron in sodium plus, right? And this will result, as you see, in decrease in atomic size for the cation and increase in atomic size for the anions, right? Okay. So this results in actually a decrease in the effective nuclear charge of the outermost electron then compared to fluorine here, and an increase in effective nuclear charge as compared to sodium, right? Because in sodium there was a 3s 1 electron, right, which was very loosely bound. So as a result we have this kind of situation, right? See, a sodium plus has decreased in size compared to sodium, the neutral atom, nearly halfway, right? Whereas this fluoride ion has doubled in size, right? You can clearly see the increase in size. So one thing you should remember, that cations are always, or should we say, the radius of cations are always less than the neutral atoms, and whereas radius of anions are greater than the neutral atoms. Now this ionization energy, another known concept, previously known to you. Now this is defined actually as the minimum amount of energy that is needed to remove an electron from an atom in its gaseous phase, right? So the ease with which an electron can be removed from an atom is measured by ionization energy. Okay, so we can write down a general equation for it. Say A is a gaseous atom and we remove an electron from this. The energy required for this is called the ionization energy. Now the first ionization energy, as it is called EI1, denoted by, is the energy required to remove the least tightly bound electron from a neutral atom. And the second ionization energy, that is EI2, is the energy required to remove the least tightly bound electron from the resulting cation, and so on. We can have third ionization energy, fourth ionization energy, and all that. Okay. Now ionization energies, one thing you have to keep in mind, is always positive, because see, from this equation you can see that this is energy is required to remove the electron. So this process is endothermic, and from thermodynamics we know that this is always positive. This is actually expressed in, more conveniently expressed in electron volts, right? In most of the books you will find it is denoted in electron volts, but it can easily be converted to kilojoules per mole by using this relation. 1 electron volt equals to what, 96.485 kilojoule per mole, and you can also convert to kilocalories if you want. Now our interest is how this vary through the periodic table, right? We are interested in the periodic properties. See, in this picture you can see the fast ionization energies of elements up to xenon is plotted here. Notice the periodic change in ionization energy. It is again peaking at the noble gases and bottoming at the alkali metals, right? Now the peaks are at the noble gases. Based on what we learned from our electronic configuration and effective nuclear charge, can we account for it? See, we will try to explain this, and from this diagram it is very clear that to a large extent the fast ionization energy of any element is determined by the energy of the highest orbital in its ground state, right? So fast ionization energies vary systematically through the periodic table. See, the variation of the pattern follows of the effective nuclear charge and there are some subtle modulations arising from the electron-electron repulsion within the same substance that we will discuss later. Now one useful approximation can be given that this ionization energy is directly proportional to the square of Z effective, that is effective nuclear charge, and inversely proportional to the square of the principal quantum number, right? Now that means this ionization energies is in strongly correlation with the atomic radii also, right? The elements that have small atomic radii generally have higher ionization energies as seen from the relation, right? This explanation is in correlation with that in a small atom an electron is close to the nucleus and experiences a strong Coulombic attraction, making it difficult to remove. Therefore, the atomic radius increases down a group, the ionization energy decreases, and the decrease in radii across a period is accompanied by the gradual increase in ionization energy. Now, if you carefully examine this chart, then we see some exceptions in the trend. See, these lines are not smooth, right? There are some humps there, there are some breaks there, right? As if the element which is on the left has a greater ionization energy than element which is on the right, right? The reverse of the trend that we just discussed. Now you can see clearly these two exceptions in the first or the second period, right? The first one is for boron and beryllium, and the second one is for oxygen and nitrogen. Let's see the first one, why it is so. See, the first one, the beryllium, has an electronic configuration of 1s2 2s2, and the boron have a configuration of 1s2 2s2 and 2p1. That means we have a change from s block to p block, right? Now this is where the exception occurs. Now we can recall about the penetration of orbitals, that 2p orbitals penetrate into the nuclear region less than the 2s orbitals. Consequently, what happens? The 1s electron shields the electron in the 2p orbital from the nuclear charge more than they shield the electron in the 2s orbital. The result is that the 2p orbitals are now higher in energy, and therefore the electron in it is easier to remove, right? And consequently they have a lower fast ionization energy, right? Now similar exceptions are there for aluminium and gallium, which are directly below boron in the group 3a. Another exception is that of nitrogen and oxygen. See here the electronic configurations, right? Although oxygen is to the right of nitrogen in the same row, it has a lower ionization energy. This exception is caused by repulsion between the electrons when they occupy the same orbital, right? Now if we examine the electronic configuration, it will be more clear that nitrogen has 3 electrons in the 3p orbital, while oxygen has 4. In nitrogen, the 2p orbitals are half filled, which makes the configuration particularly stable due to exchange energy. In oxygen, the 4th electron must pair up with any other electron, making it easier to remove because there is an electronic repulsion there. These similar exceptions occur for the same reason for sulfur and selenium also, which are directly below oxygen in the group. Now we will wrap up our discussion on ionization energies just by mentioning some aspects of second and third ionization energies. Now in this picture we see then the trend of first, second and third ionization energies of sodium and magnesium, which belongs to group 1a and group 2a respectively. For sodium, you see there is a huge jump between the first and second ionization energies. For magnesium, the ionization energy roughly doubles from first to second, but then a huge jump occurs between the second and the third ionization energies. What is the reason for these jumps? We can understand this by examining the electronic configuration of sodium and magnesium. Now let's write it. So we can write the core electrons as neon, and then 3s1 for sodium and 3s2 for magnesium. Okay. The first ionization energy of sodium involves removing the valence electron in the 3s orbital. Now let us recall that valence electrons are most loosely held than the core electrons, and that results in the ion as a noble gas configuration, which is particularly stable. Consequently, the first ionization energy is low because that leads to a stable configuration of Na plus with a noble gas configuration. The second ionization energy of sodium, however, involves removing a core electron, isn't it? It is removing a core electron, means from 2p, that is from a noble gas configuration, from an ion, right? So which has already a positive charge. So this requires tremendous amount of energy, making the value of second ionization energy very high. Now as with sodium, the first ionization of magnesium involves removing a valence electron from the 3s orbital. Fine. This requires a bit more energy than that of sodium. Why? Because as we know that it follows the trend of Z effective, that Z effective increases as we move from left to right across a row. So the first ionization energy of magnesium is higher. Fine. Now the second ionization energy of magnesium is also removed from the 3s orbital, but this time the second ionization energy is the electron is being removed from an ion with plus 1 charge, right, instead from a neutral atom. This requires roughly twice the energy of removing the first electron from the neutral atom, right? But still, it's not as high as the second ionization of the sodium, because it is being removed from the 3s orbital only, not from a noble gas configuration. Now see, the third ionization of magnesium is analogous to the second ionization of sodium. It requires removing a core electron again from a noble gas configuration. This requires tremendous amount of energy. So this makes the third ionization energy very, very high. The next property that we will be discussing is electron affinity. Now, electron affinity of an atom or ion is the energy change associated with the gaining of an electron by the atom in its gaseous state. So we can write an general equation. Suppose A is an atom in the gaseous state plus electron. We have a uninegative ion, A minus, also in the gaseous state. So electron affinity is the energy associated with this reaction. Right? Now, as we saw for the case of ionization energy, which is always positive because the process is of taking out an electron is always endothermic. In this case of electron affinity, this can either be positive or negative depending on is it endothermic or exothermic. Right? Usually it is endothermic. It has negative sign and it is exothermic process, because Coulombic attraction between the nucleus of an atom and the incoming electron usually results in release in energy as the electron is gained. For example, you see in this figure here, most of the cases it is negative sign, right? And one more important thing is, see, for the noble gases it is all positive. It is clear to understand why these noble gases have positive value of electron affinity, because they already have a stable configuration and they opposes the entrance of any extra electron in their orbitals, right? So you have to give extra energy from outside so as to produce a negative ion there. That's why they have positive electro affinities. Now if you see, the trend here is not that regular, right? As for atomic radii or electron ionization energies, right? Suppose what do you expect? We expect that as we go from top to bottom of a group, the incoming electron will be added to the next higher level, so it is far away from the nucleus, so the attraction will be lower and it will be more and more endothermic, right? Or say less exothermic, so negative value will decrease or positive value will increase, whatever, right? But you see, this trend is only followed in group 1a. For group 2a it is not followed, right? So this trend is more complicated for electron affinity than for any other properties, right? More regular trend, of course, is found when you go from left to right of a row. Based on the periodic properties that we already learned, right? What would you expect? Would you expect more energy to be released when an electron is gained by a sodium or by chlorine? Let's see. Now, for say sodium has an outer orbital configuration of 3s1 and chlorine has a configuration of 3s2 and 3p5. Because adding an electron to chlorine gives a noble gas configuration of 3s2 and 3p6, right? That means the chloride ion has a more stable configuration than the chlorine itself. Then when you are adding an electron to sodium, it does not produce a noble gas configuration. The chlorine ion electron actually experiences higher Z effective than the outermost electrons of sodium. So we expect chlorine to have more negative electron affinity, and the process should be exothermic for chlorine. This is actually the case. You can see the values. Chlorine has much more negative value than that of sodium. So for main group elements, electron affinities generally becomes more negative, that is more exothermic, as we move from left to right across the row in a periodic table. So the halogens therefore have the most negative electron affinities. Exceptions are there, of course. For example, notice that nitrogen and the other group 5a elements do not follow this general trend. These elements have ns2np3 outer electron configuration. When an electron is added to this configuration, it must pair with another electron in an already occupied p orbital, isn't it? Therefore, this repulsion between the two electrons occupying the same orbital causes the electron affinity to be more positive than that for the element in the previous column. Right. Now, due to this similar repulsion thing, see, fluorine has less negative value of electron affinity than chlorine, right? And of course the other follow those trend, but fluorine, due to its small size, and so it repels the incoming electron more than the chlorine. So the next and the last topic for today's lecture that we would discuss is electronegativity. Now, how it is defined? Electronegativity is defined as the capacity of an atom to attract the bonded pair of electron towards itself. Mind it. So important thing is bonded pair to itself. Right. So when we say that fluorine is more electronegative than hydrogen, it means that suppose there is a bond for HF, the electron pair, the two electrons that forms this bond between HF is more towards fluorine than they are towards hydrogen. Electronegativity was quantified by American chemist Linus Pauling, right? A great chemist. Now, how he did that? He compared the bond energy, the energy that is required to break a bond of heteronuclear diatomic molecules such as HF or HCl, with the bond energies of homonuclear counterparts. That means if you take the example of HF, then the homonuclear counterparts will be H2 and F2. Now the bond energies of H2 and F2 are known. They are respectively 436 kilojoule per mole and 155 kilojoule per mole. Now Pauling reasoned that if HF bond were purely covalent, that means if the electrons are shared equally, the bond energy of HF should simply be average of bond energies of H2 and F2, which would amount to 296 kilojoule per mole. However, the bond energy of HF is experimentally found to be 565 kilojoule per mole. Right? Now, Pauling suggested that the additional bond energy was due to the ionic character in the bond. Now, based on such comparison of bond energies of many compounds, right, and by arbitrarily assigning the electronegativity of 4 to fluorine. Now, this he did arbitrarily, right? So he assigned 4 to fluorine, and it was found that it was the most electronegative element in the periodic table. Now Pauling developed the electronegativity values of almost all on the periodic table by using his formula, which is written here. What is here? You see this chi as it is chi as it is pronounced. Chi A means the electronegativity of A and electronegativity of B, that is chi B. So he said that this difference is actually the square root of delta E. And what is delta E? Delta E is that difference in the bond energy that we just discussed. right? So he had his methods and he derived the electronegativity values for most of the elements in the periodic table. Now some features you can clearly see that electronegativity generally increases across a period in the periodic table. Electronegativity generally decreases along a column in the periodic table, and of course that's why fluorine is the most electronegative element and francium is the least electronegative, right? And sometimes it is also called they are electropositive. The periodic trends in electronegativity are consistent with other periodic trends we have seen. In general, electronegativity is inversely related to atomic size. The larger the atom, the less ability is to attract the electrons to itself in a chemical bond. Now, after Pauling, various persons defined electronegativity in different ways, and two more most important of them are which require mention are Mulliken electronegativity scale and Allred-Rochow electronegativity values. Right? For Mulliken, electronegativity is simply the average of ionization energy and electron affinity. Right? Whereas for Allred-Rochow is more a atomic type of electronegativity definition which takes into account the effective nuclear charge and the radius. Right? Now they have their different values and different scales, but whatever be the case, you can see in this picture, right? It's a list of this Pauling, Allred-Rochow, Mulliken and Allred-Rochow. Right? Pauling is in black, Allred-Rochow in blue, and Mulliken values are in I think the Mulliken values are in blue and the Allred-Rochow values are in red. You can clearly see that whatever be the values are different, right? Whatever be the scale, the values are of course different, but the trend is same. The trend is same. In no scale, the fluorine is less electronegative than chlorine, right? So these are some aspects of electronegativity. So we learned today, right? And lastly, one more point about electronegativity, right? About how it affects the bond properties. Right? Suppose you have a bond between A and B. Now there can be three situations. First, electronegativity of A is equal to electronegativity of B. In such case, electronegativity of A is less than electronegativity of B, and electronegativity of A is very less than electronegativity of B. Now in these three cases, the first one, what will happen? The bond pair will be equally shared and it will be in between. In this case, we say the bond is pure covalent, right? In fact, we cannot have a substance like this, A and B. Wherever there is exactly, the electron pair is exactly in between, A and B should be the same atom. The homonuclear molecules like H2, O2, F2, they are all fall in this class. Next, if it is slightly different, then there is a delta negative charge on the B, and we say the bond is polar covalent. And lastly, when there is a great difference in electronegativity, the bonded pair is completely transferred to atom B, and which acquires a full negative charge, whereas the atom A acquires a positive charge. In this case, we say it is ionic bond. So with this we end today's lecture. In the next class we'll talk about polarization and hard and soft theories.